Okay, so good morning, everyone. I'll start with the last lecture. So last time I defined for a sheaf or a complex of sheaves F, in fact for F in the derived category of sheaves, something which was called the singular support of F. And the idea of the singular support is that it tells you in which direction the sheaf changes. So you're at a point and you're looking at different directions, moving a little bit in different directions, and you say, well, in this direction nothing changes. I mean, the sheaf, if I move in this direction, is not going to change, but in this other direction it's going to change, and that's what the singular support is about. So remember that the definition is that x0 psi 0 does not belong to the singular support of F if and only if for any x and psi, so this is in T star x near x0 psi 0, and for any function phi such that the differential of phi at x is psi, we have an isomorphism from the cohomology of U, well, the limit for U containing x of the cohomology of U with coefficients in the sheaves to the cohomology of U intersection phi strictly negative. And this is again the limit for U containing x. To the normal support of a function? To the support of the function? No, it's possible to relate it with the support of the sheaf, in the sense that the singular support, when you project it on the base, so is contained in pi minus 1 of the support of F. So of course, if you're outside the support, the sheaf is just 0, and so when you move from a point where in a neighborhood of a point where the sheaf is 0, nothing changes, so you're not in the singular support there. So to be in the singular support, you already have to be on the support, okay? But of course, it's more precise than that. It's very close to the microlocal point of view. Moreover, this contains the 0 section. So the set of point x0 with x in the support. Does this answer your question? Yeah.
Can you remind very quickly what is the definition of support of F?
Support of F is the set where you have sections which are not 0. So x does not belong to the support of F, is equivalent to saying that, well, F of x is 0, sorry. Too many negative here. And these are germs, so it means that in a neighborhood of x, all the sections are essentially 0. Okay. So last time we saw some examples. And let me just write this. The first one, that if you take a function and you look at the constant sheaf over the set F negative, then the singular support of this is just, well, the zero section over f negative, and the set of x lambda df of x, such that lambda is negative and x belongs to, and f of x is 0. And that works if 0 is a regular value of f. And the second example, which was a little bit more complicated, was the following. Assume I have a generating function s, so s of x and psi, generating function, and I'm looking at the set u sub s, which is the set of x, psi, and lambda, such that s of x psi is less than lambda. And then I look at the projection from x times rk times r to x times r here. And I'm looking at the sheaf f sub s, which is, well, I would take pi star, but because I'm in the derived category, I have to take r pi star. Of the constant sheaf over the set us, and then the singular support of f sub s is something which I call L hat s. So L hat s, by assumption, should be in T star of x times r. And so L hat s is just the set of points x, s of x and psi ds over dx of x psi, and this is tau, such that tau is positive and ds over d psi over x psi is 0. And if you remember, the Lagrangian submanifold associated to the generating function is something very close to that. It's just the set of x ds over dx of x psi, such that ds over d psi of x psi is 0. So what's the difference? Well, one thing you immediately see is that if you project this if you take the obvious projection from T star of x times r to T times of x, then L hat s projects to Ls. So L hat s can be seen as a lift of Ls. And essentially, it's the only lift that has the property that you may have noticed, that this is homogeneous. I think I missed, sorry, the tau does not go here. The tau goes here. So tau applies to ds over dx, not to s. And it's the only lift that is homogeneous, okay, in the cotangent variables. So you have variables x and p, and something is homogeneous in p if whenever xp is in the set, then x lambda p is also in the set. And then L hat s is first homogeneous and second project on Ls, and this essentially defines L hat s. There's another way of getting Ls from L hat s. You can say that Ls is also the reduction of L hat s by the coisotropic subspace tau equal 1. If you take tau equal 1 here, and you forget, then you're going to forget this variable, and you get back to Ls. So I'm not going to prove that. It's a sort of, there's a calculus of this singular support, which tells you how this singular support behaves when you apply these derived functors. And this gives you this, this result. So it will tell you that if you take the if you have the singular support here and you apply, if you have a sheaf here and apply r pi star, then the singular support of the new sheaf is the symplectic reduction of the singular support of this sheaf here. In this situation, that's exactly what it's going to tell you. So this is the standard. So the remark I wanted to make about the about the singular support is that indeed the singular support of F is always homogeneous. Well, look at the definition here. If I change psi to lambda psi, well, I can just take phi, replace phi by lambda times phi, but then for lambda positive. So it's positively homogeneous, sorry. And then the set phi negative doesn't change, of course. So it's positively homogeneous. So you could think, well, this is not so good because we wanted to start from a Lagrangian submanifold and construct a sheaf such that the singular support, I mean, that's what I was sort of hinting. You want to construct some sheaf such that the singular support of the sheaf or the complex of sheaf is equal to L. But you can only do that if L is homogeneous. So the idea is that you're not going to do that for L. So we are going to look for a sheaf F star, which I write F star L, such that the singular support of F star L is L hat. And here L hat is just the set of X T, P, and tau, such that X, P over tau belongs to L. Tau is positive, and T is equal to F of X and P over tau, sorry. Whereas small f is PDX over L. So the form PDX is the Liouville form over L is exact, so it's the differential of some function f. And I use this function f here to describe this lift L hat. And, and you see that by definition, this is positively homogeneous. So L hat is positively homogeneous. So at least you have a chance to solve this problem here. And you can check that if L is LS, this L hat is exactly the construction that I gave here. I'm trying to think about something important to write here, but it's too early because this goes up, actually. So what I absolutely have not told you is what. So the second remark is that the singular support of F is coisotropic. And this is a theorem by Kashiwara and Schapira. And there's also a more algebraic proof. I mean, for my taste, the Kashiwara-Schapira proof was algebraic enough. But if you want even more algebraic, there's a proof by Gaber of that. So I put here coisotropic in a sort of vague sense because the singular support of F is not a smooth manifold in general. So it has singularities, and so you have to define what it means to be coisotropic for a singular manifold. But there's a way to define that. That's the first thing. And the second thing is that actually, in our case, we will only manipulate smooth singular supports. So a priori, our singular supports will be smooth. And so we don't really have to worry about that. What you may have to worry is about this coisotropic, because coisotropic, of course, is not Lagrangian. So the question is the singular support of F Lagrangian, and the answer is yes if F is a constructible sheaf. So I don't want to explain in details what constructible sheaf means, but it means that there's a stratification of the space over which the such that on each strata the sheaf is locally constant. So this means that it's locally constant on the strata of some stratification of the space. Well, I don't want to get into too much detail. I think one standard way is to say that you take an analytic, well, if you're dealing only with one sheaf, it doesn't matter so much what stratification means. I mean, you can say in the sense of Whitney or whatever. But when you start to have several stratification, then you get in complicated situations, because you have to see how one stratification behaves with respect to the other. And then usually people ask that objects are analytic.
What do you mean? What is an example of constructible sheaf?
Well, actually, for a generic S here, these sheaves over there are going to be constructible. And, and in fact, if you're looking at the manifold LS, so the generated manifold, you look at the projection on the base, and at least if L is in general position, you have singularities of the projection which make a stratification. And this is going to be a stratification of the... I guess what I should have said... well, I will mention that later. So the questions that I'm going to try to answer now are the following. So given L exact Lagrangian in T star X, so this is one, can one find an F, well, in the derived category, but actually you're going to the derived category of X times R such that the singular support of F is exactly L hat. That's the first question. And the second question is F unique. So I can immediately answer the second question, in that the answer is no, because if you look at the singular support, for example, of F plus F, this is the same as the singular support of F. That's not very hard to see. So clearly you cannot have uniqueness. However, there is a condition because if you think about what this should be, in fact, the singular support of F plus F should be 2 copies of the singular support of F. Except, so if you think of it in terms of algebraic geometry, it should, except that we're in a situation where that it doesn't mean anything to have twice the same point. I mean, you move in one direction and see whether the sheaf changes or not. Okay? And it doesn't make much sense to say whether this point is doubly covered or simply covered. I mean, there's nothing like that. But on the sheaf, you can impose a condition which is called simple. So if you have simple sheaves, then this excludes this difficulty, and one has uniqueness. So in a certain way, this is the only difficulty that, I mean, or the only kind of difficulty that can occur. And in fact, you have to also impose some other property at infinity, but I'm not going to mention that. Okay, so now the question is how does one construct FL? So there are two situations. So the first situation is the case where L is the image by phi of the zero section, and phi is a Hamiltonian isotopy. So this is done, for instance, in the paper by Guillermou, Kashiwara and Schapira, and also is related to some previous work by Tamarkin. So the way the Guillermou, Kashiwara, and Schapira do it is actually different from what I'm going to explain. What I'm going to explain is exactly the parallel of what we did to construct generating functions. So formally, what could you say? Well, you could say, I know that phi of 0n has a generating function, which moreover is quadratic at infinity. So let's go, it's S. And that if I'm looking at the sheaf F sub S, which is this R pi star of KUS, then the singular support of F sub S is just L hat of S, which is what I want. So you could say you have the proof is just the proof using generating functions. Okay? Now, this is not the way they do it, and there's a reason for doing it differently, in the sense that we want actually not to quantize not so much, so this is called quantization. Sorry, I used this word. So quantization is the operation of going from L to F, so from the Lagrangian to the sheaf. So what we would like to show is that if you start from L0, and L0 has a sheaf, is the singular support of some sheaf, and you apply some Hamiltonian transformation, then phi of L0 also is the singular support of some other sheaf. Okay. So what we want to show is that if L0 is the singular support of F0, and phi is a Hamiltonian map, then there exists F1, so this is L hat 0, such that the singular support of F1 is L hat 1. And there are many reasons to do that. I mean, first, there's a sort of it's aesthetically more satisfying. But also, when you want, for example, to quantize general exact manifolds, usually you need some general position situation. Okay. So assume you have a Lagrangian, which is given Lagrangian, and you say, well, I want to find a sheaf, which is such that L is a singular support, and L is not of this type here. It's not of the type phi of 0 L. Okay. So I take this L, and I say, okay, I can do this operation provided L is in general position with respect to the projection. But what happens is that it could very well happen that you start from an L which is not in general position with respect to the projection. So what do? Well, you apply some small Hamiltonian isotopy, and this will put your Lagrangian into general position. But then you have to say, well, I start from now I have something, so the perturbed Lagrangian is the singular support of some sheaf. Is the original Lagrangian, the one which was not in general position, also the singular support of something? Okay. Well, if you can do this operation, so F0 will be the one in general position. So L0 is the one in general position. L1 is the one you want to reach. Okay? And you sort of go back by this operation, by going back by the Hamiltonian deformation that you can lift to the sheaf level, and you then can go from F0 to F1, and you know that you can find the generating a quantized sheaf. Okay? So that's one reason why you need that. And so the idea is that what you're doing is actually quantization of map. So if you have a map phi, which is symplectic from T star x to T star x, then you should, well, I will write this K sub phi, which should be a map from the sheaf over x times r to the sheaf over x times r. And actually, it's not the sheaf, but it's the derived category here, and it's the derived category here. Yes, it should be. Yes, it's a functor in the sense that so that k of phi composed with psi is k phi composed with k psi. So there's a first, well, let me go to the next blackboard. So the idea is that K is constructed as a kernel, and pretty much like, so there's a parallel between this this approach to sheaves and the theory of what I would say of differential operators. Or functional calculus, whatever. So the idea is the idea of a kernel, and the kernel is what? It's some element k in some derived category of sheaves over x times y. So here what you should think of, I mean, it's just formally related, is the idea that if you have a function f over y, you can associate this function here. So this is an operator given by the kernel k. And formally, what I'm going to do here is exactly the same as this thing here. And so the operator now is given as follows. So let's call it k tilde. So this is going to go from the derived category of sheaves over x to the derived category of sheaves over y. And it's given by some unpleasant formula with lots of R of objects here, lots of derived. So this is the formally correct expression. So Qx and Qy are, of course, the projection here. Well, if you have two sheaves, you can look at you can apply the homomorphism, and this also has a derived functor. I mean, homomorphism to something is a functor, and this has a derived functor. What I have not defined is what this is. And actually, I'm not going to define it precisely. But so Qx star, shriek, sorry, is the compact supported version of Qx minus 1. But I have not told you what Qx minus 1 is. Now, if f is a map from x to y, there's a functor f minus 1 on which sends a sheaf over y to a sheaf over x. And how does it work? Well, f minus 1 of g is the sheaf associated to the following pre-sheaf, the one which sends u to the limit for v containing f of u of g of v. So basically, there's only one way to construct an inverse image from sheaves to y to sheaves to x. The obvious construction only gives you a pre-sheaf. I mean, this is only a pre-sheaf. And then the only thing you can do at that point is to replace the pre-sheaf by a sheaf. So of course, it looks a little bit abstract, but f minus 1 as a good property is an exact functor. So the definition is complicated, but then the properties are simple from the sheaves over y to the sheaves over x. So what am I doing here? I have a sheaf f over x. So maybe I should, yeah. I have a sheaf here over x. I'm lifting it to x times y by this operation here. Then I'm looking up to this derived category to the morphism between K, which lives in the sheaves from X on X times Y, to this sheaf, which also lives on X times Y. And then I reproject back. Here, QY star is going to be the projection, so on X times Y, to Y. And if you think about that, that's exactly what you're doing here. I mean, I look at f of y. I consider f as a function over x times y. I multiply it by k. And then I sort of reprojecting back. Reprojecting back corresponds to integrating here. And then I get a function of y. It's exactly the same idea. And so there's a calculus on these kernels. In particular, there's a nice property is that the singular support of K composed of K of F is the singular support of K composed with the singular support of F. And now the singular support of K you can see as a correspondence, as a Lagrangian correspondence, and it has this nice property that so sorry, how I wrote this as K tilde. So if you apply this quantization, it just behaves in a natural way with respect to the singular support. I omitted a certain number of assumptions that you have to make on K tilde so that it really behaves well, or on K, okay, some sort of regularity. Some questions? Composition on the right-hand side is the composition of Lagrangian given by Lagrangian correspondences. Okay. So yeah, that I explained before. So this, of course, this works in the case where this is, yes. Okay. So what's the idea now? You have this calculus of kernels. And so what you would like to do is to, if you have a map phi, you would like to construct some kernel K of phi, and such that the singular support of K tilde of phi is just the graph of the map phi. Well, there's a first step where you have to make everything homogeneous. Okay, I will sort of skip that. You have to go from the map phi, which goes from, let's say, T star x to T star x, to a map capital phi, which goes from T star x times r to T times x times r, and such that capital phi is homogeneous. This is not hard to do. So what you're actually quantizing are, of course, homogeneous objects, because all the objects here are homogeneous. But really the important thing is the underlying phi. And so what you want is to go from phi to k of phi. And what you can do is to use the same argument I use for generating function. To say, well, it's enough if I can do it for very special maps, phi h, okay, provided I can do it in a sort of neighborhood of the map. So I can just take maps of the type phi h, well, remember that phi h of Q1, P1 is Q2, P2, meant that P1 is dH over dQ1, and P2 is minus dH over dQ2. So this sort of twist map. So if I can quantize phi h, this is good enough because then I use the calculus of kernels and use the composition, and then I'm going to get whatever, to be able to quantize whatever I want. And now to quantize phi h is actually quite easy. Because it's, you can just take the kernel here of K sub W of H, where W of H is just the set of small q, capital, let's say Q1, Q2, T1, T2, such that H of Q1, Q2 is less than T2 minus T1. And you could check that that's not very hard to see, that the singular support of KWH is actually the lift capital phi h of phi h. So you just have to quantize very simple maps. And once you quantize very simple maps, or I mean a small family of maps, the map of type phi h, then you know that you're going to be able to quantize everything by just this calculus of kernels. Yes?
How is capital phi related to phi? Is there some sort of
There's essentially only one.
leaf and symplectic
Yeah, it's contact leaf and symplectic leaf. You can see it this way. I could even give you formulas.
homogeneous? You can use the phi h.
Yes. So this homogeneous means that phi of z lambda psi is lambda phi of z psi. Sorry? This is the lift of phi a, of small phi h. So this is because you have to go to the homogeneous object. And it's, oh, sorry, you said it's a graph. Yes, of course, the graph of phi h. It's Hamiltonian, yes. So here phi, indeed, it's Hamiltonian. Okay, so that's one case somehow. Now let me, are there any questions so far? So now let me go to second case. Which is a general L, so I still assume that L is exact. And well, in principle, I should also assume that it has vanishing Maslov class. But there is a theorem by Thomas Krag which tells you that any exact Lagrangian in T star n has a vanishing Maslov class. So, but that's automatic. However, this is a very hard result. So what do I have now? Well, I have a general Lagrangian here. So this is the base. And I want to construct a sheaf F sub L, which lives in, well, the derived category, but at least, say, the sheaves over X times R. So one thing you could start asking is take a point X here. So of course the sheaf is not really determined by the germs, okay? But at least if you know what the sheaf is, you should be able to say what the germ is at the point X. So what is and very often, if you know what the germ is over any point, and you know somehow what kind of continuity you should expect from the sections, then you can actually understand what the sheaf itself is. So the question is, what is this torque here? Well, you can try to guess, and the only way you can guess is by going back to the only case you can actually do is the case where you have a generating function. So if generating function quadratic at infinity, let's say S, then F sub S is this R pi star of K U sub S. So maybe I should start by looking at the case where there is no maybe I should look at the case where there is no psi variable, so I just have a function S of X. So in this case, well, so this is the graph of my function ds. Okay. And the sheaf f of s is just the sheaf, the constant sheaf over s of x less than lambda. So it's just going to be, now it's easier to draw the function s instead of ds. And then it's just this constant sheaf here. Constant sheaf over s less than lambda is just the region below the graph of s. And so the sheaf is just constant here and 0 here. And so if you look at what happened here, so this is on x times r, what you're going to get is you get the constant sheaf below the value s of x and the 0 sheaf above. Get this constant sheaf. Now, if you take k of us, of course, it's the same, except that you also have psi variables. And then you have to understand what happens when you apply this r pi star. So when I apply this r pi star, I'm going to get a complex of sheaves a priori. So for f, general f of s, okay, so this is, you should see this as a complex of sheaves. You can actually prove that not the germ, sorry. If I'm looking at this quantity here, the cohomology of over x times AB of f dot s, this is going to be equal to the cohomology of Sxb mod Sxa. So remember that, so S sub x is just the restriction of S to x times Rk. So I just freeze the first variable. And Sx lambda is just the set of xi such that Sx xi is less than lambda. So why am I doing that? Well, it's just convenient. My sheaf Fs is a sheaf over the product of x and r. In principle, when I look at the germ, I should look at the germ over a point xt. But I can also look at the germ over a point over a set, so x times some interval ab. And somehow, this is more natural or easier to deal with in this situation. Okay. It's geometrically more. So of course, otherwise I would have to take, so for each t, you would have to take the limit as b goes to t from upper value and a goes to t from lower value and see the limit. And so what you would get is 0 if the value is regular and something which is non-zero if the value is a critical value. But somehow it's easier to pack this together over values a and b. And this is essentially what's behind the Loresser spectral sequence, this identification. Okay, so what do I have? I have this sheaf f dot s, and the information I have on this sheaf is that the cohomology of this sheaf over this set here is the cohomology of Sxb and Sxa. And if I'm doing something reasonable, what I should for general L is to construct Fl for general L such that if L is Ls, then we have the same property so that H, the cohomology of X times AB and FL is the cohomology of Sxb, Sxa. So the question is already how do you, what's the analog of this on a general manifold? If I don't have, a priori I don't have an S, so what is the geometric meaning of this? The geometric meaning of this is the following. So let's call Vx this vertical here. So Vx is a Lagrangian submanifold, just x times Rn star. And my claim is that this quantity here is in fact the Floer homology between values A and B, or I should take open set maybe, A and B, of L intersection with Vx. So what does it mean? Well, it means I'm going to build a complex, the Floer complex, where the generators are going to be the intersection points here. So in this situation, it's going to be these three intersection points. And the boundary map are going to be obtained by counting holomorphic curves connecting, for example, these 2 points with one boundary on V and the other boundary on L. Okay. And you could say, well, this is not very nice because, of course, L is compact, but V is not compact, so you're going to get in trouble. But in fact, you don't get in trouble because only one of them is non-compact, and the non-compact part sort of goes to infinity. And so that's something you can actually do. Okay. And so as I explained last time, you can use the filtration by the action functional. And so you can say what the Floer homology between level A and level B is. And it's exactly going to be the same as here. And why should it be the same as here? Well, because if you're looking at the critical points of the function S sub x, you see that they're going to be exactly the points where ds over dxi is 0. Okay. And the points where ds over dxi is 0 are exactly for x fixed, are exactly the points of L which are above the point x. Okay? So the set of xi such that ds over dxi of x xi is 0 is in one-to-one correspondence with L intersection, Ls intersection with Vx, of course. I mean, each point with ds over dxi is 0 gives you a point ds over dx. Okay? And so you have exactly how many points. So it tells you at least that the generators are the same. And then to say that the cohomology are indeed the same requires some more work, because then you have to deal with the boundary map. And but that's essentially what I told you last time, that the cohomology of the generating function is the same as the cohomology for the Floer complex. Okay. So I'm still far from done in a way, because I know what the cohomology of this sort of germ near x times AB should be, okay? But I don't know what the complex is. And of course, given a cohomology, you can have lots of complexes which have the same cohomology, and there's a priori no canonical choice. But in this situation, because you know all this cohomology between A and B, and you also know the maps when you vary A and B, what I claim is that there's a way to recover a complex, a canonical complex, which will have the correct cohomology. And this is what's called the Morse-Baranikov complex, which I'm now going to explain. Actually, it really fits here. So the idea of this Morse-Baranikov complex, there are two ideas. One is that there are complexes which are nicer than others, which are called simple complexes. And these are complexes such that you can find the base, such that the boundary map sends the generator either to 0 or to generator. So a simple complex CD means there exists a basis EG, E sub G, such that the boundary of EG is either 0 or some other generator EK. Of course, I mean, you have to choose the right basis. So that's the first idea. The second idea is that now assume you have a function f, which is a Morse function with distinct critical values. And because I have distinct critical values, I will be able to identify critical points and critical values. So then there exists a filtered simple complex, which I will call B C star. Such that if I'm looking at the cohomology between level B and level A, this is the same as the cohomology of BC star between level B and level A with bound. Okay. So what I mean is that BC star has a filtration. So there's, you can write BC star of B, which is the set of E in BC star, such that I will still call F the filtration, so F of E is less than B. And then BC star of B, you will see in a second, I mean, this is probably not very clear, but you will see in a second how you construct this complex, and then it will be clear what happens. And this is just the quotient BC star B over BC star A. And of course, when you write such filtration, it assumes that the boundary map respects the filtration. I mean, is increasing. And the idea is that you not only have the knowledge of this cohomology of FB and FA, but you also have maps between the FCFB and FCFA and so on. So how do you construct this? This construction of BC star, maybe I should call it BC star F, it depends on F. So I'm going to take a generator, of course, for each critical point. So the generator CG for each critical, and I will even say it for each critical value. It's going to be easier. And then I'm going to look at the map so it's a Morse function, so the cohomology of f Cj plus epsilon and mod f Cj minus epsilon is one-dimensional. So now there are two possibilities. If I'm looking at the cohomology of f infinity mod f Cg minus epsilon, so f infinity means just I take very large values. So I look at all the cohomology that's above level f Cg minus epsilon, and I look whether I can induce the class I have here. So here I have only one class. So if this map is on 2, then I write boundary of Cj is 0. So here I identify the generator with the critical value. Well, if this is not true, it means that at some point my class here is not anymore induced. So of course, if I increase this number here, well, at the beginning, the class will, of course, be induced before I reach any other critical value. I'm certainly going to get an isomorphism here. And then this cohomology is going to change. I know that when I get here, the unique generator here is not anymore in the image. So there's the last moment where you're still in the image. So if Ck is the smallest c such that the cohomology of fcg minus epsilon does not have something in the image here so that this is 0, then we set that the boundary of Cj is Ck. So of course this respects the filtration because it's clear that Ck is going to be larger than Cj in this situation. So let me give you an example. Well, look at this function here. I have three critical values, one here, one here, one here. So my complex is going to have 3 points somehow. I mean, 3 generators, one here, one here, one here. When I look at this cohomology class here, corresponding to the minimum, this corresponds to the minimum. So I can increase this here. I will always induce this cohomology class here by restriction. So this one must have boundary 0. Now, if I'm looking at this one here, well, between this level here and this level here, of course, I induce the cohomology class. But then when I get here, these classes sort of cancel. And so in between these two levels, there's no cohomology anymore. So this class cannot be induced by anything between here and here. Okay. Between here and here, there's no cohomology. So necessarily, I have a boundary which goes like this. And this is a canonical choice. You have to be careful about one thing, is that it can depend on the choice of the field of coefficients. Okay? Because I sort of assume that I have a field somewhere by saying that the map is either onto or is 0. Okay? Otherwise, the image could be some torsion subset or something else. Okay? So I have to assume I have coefficients in a field. And this construction can depend. I mean, there are examples in this paper by Baranikov where he shows by taking 2 different fields, you get 2 different complexes here. Okay? But, I mean, that doesn't matter so much. So what's the idea again? So I have this L here. And so I have this Floer cohomology between A and B of L and Vx. And of course, I have the same induced map if I have several levels, A, B, and C. I also have the restriction map from the cohomology between level A and C to the cohomology between level A and B. Exactly the analog of this map here. So we have restriction maps. Okay. So formally, again, once you choose a field of coefficients here, you can define this Baranikov complex BC star L. And this is well defined over, let's say, x times r. So for each x here, so the plane is, in fact, I should represent the what I haven't done here, but the wavefront set. So this is the projection. Here I have the projection of L hat on X times R. And that's what it looks like. That's some singularity. This should not be the same. So I have a point here. So now this is the set. So X times R is the set where the sheaf is going to live. That's one reason to represent it this way. And now on every X, I constructed this simple complex. So the simple complex will correspond to point here. So generator will be point here. And then I will have connecting, I will have the boundary map here. So the boundary map, for instance, on this picture is going to be something like that. So it's going to connect these 2 points. And it's not going to do anything with this one as boundary 0. No, you don't have a Morse function, but you have the lift. You have a wavefront set. Because you have the lift of the either the function S if you had a generating function, or the primitive of PDX. So the last coordinate here is the primitive of PDX. Oh, just the one coming from the Fleur action. So you're looking at the map from AB and AC. You do everything in Fleur homology. You have the same map, and you can say for each generator, so each generator corresponds to a point above X. Okay? And so either here or here. And then what you have is that this complex will have arrows which I could represent here, for instance, or I could represent on the other picture. So one, for instance, one could be represented. You can represent the picture either here or on the other side here. Sorry. It takes longer to. Okay. So this I only represented for fixed X. And now I have to sort of move around and see what happens and define what the complex of sheaves is going to be. So I already hinted to the fact that over X times over a point X, this complex is going to be this Baranikov-Morse complex obtained from Fleur homology. So there's a way of doing that. So here I have the Lagrangian, and let me represent, actually I will make something simpler. Something like this. So this is X again. Now this is R. And I'm going to put some point X here. And I have these 3 points here, which corresponds to these 3 points here. And now the boundary map is in the Baranikov complex is something like this here. So now I have to say what happens on an open set. And because I'm talking about sheaves, it's enough to talk about small open sets. So in the vertical direction, I already know everything. I mean, I already know what the complex is over here. What I have to do is to extend a little bit in the basis direction. So if I'm at the generic points, it's pretty obvious because So what is the complex going to be? Well, it's going to be, so over this point is going to be the constant sheaf. So let me maybe enlarge here. So here what I see are, so I have something like this, and then a third one. Coming like this. So in the neighborhood of this vertical line here, the only thing I see are these three pieces here. And then, so what my sheaf is going to be, well, one sheaf is going to be the constant sheaf here. The second one is going to be the constant sheaf over here. And the third one, if I can find some blue chalk, yes. The third one is going to be the constant sheaf over here. So I'm sorry, I'm using, it's easier to draw the opposite convention. Usually I use, before I use the subgraph, now I use the epigraph, but it doesn't change anything. So I have, for each generator here, so for a point here, I can consider the constant section here, for this point here, the constant section here, for this point here, the constant section above, and how these three, so if I'm, let's call A, capital B, and capital C, these regions. So I have the region Ka, Kb, and Kc. So my total complex is going to be the sum here. And I have to say what the boundary map does. And the boundary map I sort of somehow described, because it's going to send this one to this one here. So the D is going to be send Kb to Kc, and there's a sort of obvious way of mapping Kb to Kc. And it's going to, Ka. And it's going to map Kc to 0. So the boundary map that you have on these points here obviously extend because each point corresponds to a sheaf here. So defines you the complex of sheaves. So there's a sort of obvious way of defining the complex of sheaves. And so I said, well, that's what happens over one point here, but now it's clear what's going to happen globally. So on this small picture, well, the Ka is all this, Kb is all this, Kc, well, sorry, Ka is everything above here, Kb everything above here, and Kc everything above here, or a sheaf supported on these three sets A and B and C. And now clearly this map, okay, is clearly defined. So by sort of the obvious continuity here is pretty transparent. So this is not so difficult, and it's also not hard to prove that the singular support of BC star L is L hat at least over the generic points. So at least over this region here, like here, it's not hard to see that the singular support is just L, but that's just because the singular support of Ka, it has to be contained in the sum of the singular supports here, the singular support of K and the Kb and Kc, and the singular support of Ka, Kb, and Kc are exactly given by these three sets. Okay, so in that case, it's almost obvious. Where things become a little bit trickier is when you get here, or when you get here. Well, the reason is that when you get here or you get here, which corresponds, for example, to getting, one of them corresponds to getting here. Okay. You're going to have, when you're looking at the Floer action or you're looking at the generating function, either it doesn't have all distinct critical points, so two critical values, two critical values can coincide. That's what happens here. Or you can have the elimination of two critical points, which means that at the moment where they eliminate, it's not a Morse function anymore. That's what happens here. And I don't really have time to explain that. In the one-dimensional picture, it's not hard to see. See, the crucial point is that this canonical complex I define is exactly going to send this point to this point. So when they get closer, they sort of cancel each other in a natural way. And so everything works fine here. You don't get any trouble. And you have to be a little bit careful about what happens here as well. Okay? But in one dimension, it's pretty straightforward. And what you have to prove, so one has to prove that this sheaf BC star L extends to the singular part of, let's say, to the singular part of the wavefront set, which is more complicated. So that's the only difficulty. What's easy to see is that whatever way you extend it, the singular support will contain L hat. That's because it's closed, so this is going to be closed set. And coincides with L hat above a set of codimension. Well, either 1 or 2, depends how careful you are. At least 1. And so what you have to prove is that actually this construction does not add extra points to this singular support. That's where you have to be a little bit careful. And as I mentioned before, in order to do all this construction, you need to start from something which is in general position. If I wasn't in general position, I could not define this BC star L for an open set of L. Okay. And that's where you need the first case, where you first put things in general position by applying some Hamiltonian deformation and show that it's enough to prove for the result for something in general position, and then you use this construction to do that. And okay, I think I will stop here. Thank you very much for your attention. And maybe before I conclude, I would like to thank the organizer for this wonderful conference. It was very, very nice and pleasant being here in Grenoble. And the organization was just perfect. So thank you very much for organizing.